And as shown on that intro slide, we're making products that are conjugated. So as a reminder, conjugation is something like this, where you have a double bond, a single bond, a double bond, right? So you don't want two double bonds in a row, but double bond, single bond, double bond. That leads to increased stability, sort of similar to aromaticity, but not quite as extreme, I would say. And then we'll also be talking about an intramolecular variant. And so reminding ourselves that 5 and 6 membered rings are the easiest to form. So when we're doing intramolecular reactions, we want to be making 5 and 6 membered rings. But today is all about the Aldol reaction. So we have 4 learning objectives that are basically 4 variants of the Aldol reaction. And so the first one is called Aldol addition, and then Aldol condensation, and then mixed Aldol. So they are just different versions of the same reaction, but it's really just one reaction. So let's get started with our first learning objective, which is the 4 Ps for the formation of the Aldol addition product from aldehydes and base. This is section 21.2. All right, so the overall reaction is an aldehyde kind of reacting with itself. So we're used to aldehydes acting as an electrophile, right? We've had a whole chapter on aldehydes and ketones acting as an electrophile. So we are, again, going to have an aldehyde reacting as an electrophile, but we're also going to have that aldehyde being the nucleophile, because on Friday, we learned about enolates, right? And how you can make a nucleophilic form of an aldehyde in the presence of base. And so we're literally just going to react those two things together. So when we react an aldehyde as an electrophile, we form an alcohol. Our nucleophile should be attached here. And when we use the nucleophilic form, an enolate, it is attached by the alpha position. So this is our Aldol addition product. So why is it called Aldol? Well, if we look at the structure of this product, right, we have an aldehyde. Oops. So the ald part is from aldehyde, and we have an alcohol. So the all part is from the alcohol. So aldol just means that the product has an aldehyde and an alcohol. Could also be a ketone and an aldehyde, but it works a lot better with aldehydes. So if we're using OH minus as the base, right? So sodium hydroxide, potassium hydroxide, that's kind of the most common. This is a reversible reaction. So for aldehydes, our equilibrium favors the products. But for ketones, it favors our starting materials. So if I were to draw the same equilibrium with, say, acetone, we know that ketones can also be electrophiles. If they have alpha protons, they can also be nucleophiles. So we draw the same equilibrium in the presence of sodium hydroxide. Our aldol addition product would look like this. But because it's a ketone, it's actually not favored to go to the product. So we actually only get about 2% of this product at equilibrium. So that means we have 98% of the starting materials. Okay. So technically, it could happen for both aldehydes and ketones, but normally it's aldehydes just because of the equilibrium. All right, so let's go over the mechanism again. It just looks weird, but it's all things that you already know how to do. So this chapter is enolates as nucleophiles. So we are first going to generate our nucleophile. So here's our aldehyde. We need those alpha protons, right? So remember, alpha is the position next to the carbonyl. So we need at least one alpha proton such that we can deprotonate it using our base. So let's use potassium hydroxide in this case. Okay, so first we need to generate our nucleophile by deprotonating that alpha proton. Push our electrons up into the oxygen. Like so. So remember, this is the resonance structure that we want to draw for enolates because it's the most stable one. But just as a reminder, we do have another resonance structure where you could also draw that negative charge in the alpha position. But we're going to use the one on the left as our nucleophile because that's normally how we draw it. But this just shows you why that alpha position is the most nucleophilic position. All right, now we have a nucleophile. And then that nucleophile is going to attack our electrophile, which is our aldehyde. So when we identify our nucleophile, we know that it is our enolate. Our electrophile is going to be that carbonyl carbon, just like every other reaction when we are using aldehydes as our electrophile. So this is the weird arrow pushing that I mentioned on Friday, right? Enolates always attack by that oxygen lone pair pushing down, and then that carbon-carbon double bond being the thing that goes out and attacks, and then we break the weakest bond. Okay. So just like every other time we have attacked an aldehyde under basic conditions, right? We form this alkoxide. And then we've attached our nucleophile to that carbonyl carbon. Looks like that. And then to get to the final product, all we need to do is protonate that alkoxide using water. So there's our aldol addition product, and we have regenerated our base. So again, it is catalytic in base. Okay, so let's walk through that one more time. Step one, enolate formation. Make your nucleophile. Step two, nucleophile attacks electrophile. Just like every other reaction we've ever learned. It's just a weird looking nucleophile, right? So remember our weird arrow pushing, that we're going to push down oxygen lone pair, and then CC double bond attacks. That's just the particular way that this weird looking nucleophile attacks. But it's not really any different than any other reaction that we've learned. And then our last step is just protonation to get rid of that negative charge. Questions on that? Yeah. This one? It's still there. I just didn't draw it out. right? It's still right there. Yep. Yeah, remember if there's no charges, right? We assume that CH bonds are there to make the carbons neutral. Good question. Other questions? Okay, it's not different. It's a nucleophile attacking an aldehyde, but it just is a weird looking nucleophile. Okay, so that's our aldol addition. So now let's look at aldol condensation. So this is our next learning objective, which is the 4 Ps for the formation of alpha, beta unsaturated aldehydes from aldol condensation. Okay, so aldol condensation has aldol in the name because aldol addition is the first half of the mechanism. And so we're going to start from the aldol addition product that we just made. So you will usually see it from the very beginning, but because we just went through aldol addition, I'm starting kind of halfway through. So once we have this aldol addition product, we can then do the condensation reaction. So in a condensation reaction, you lose a small molecule. In this case, we lose water. We essentially lose the OH, the alcohol, and another alpha proton to get us. Oops, let's try that better. This. Okay. So we lost our OH, we lost another H, and we put a double bond right here, right there. Okay, so this is our aldol condensation product, which is also called an alpha beta unsaturated aldehyde. So alpha beta is just telling us the position of the double bond. So alpha beta unsaturated means the position of the double bond. And then again, we lost water in this process. Okay, so that's our overall reaction for the condensation. We have to lose water. Okay, so now it's really important that this is not E1 or E2. Okay, so you've learned other condensation reactions, E1 and E2, right? Elimination. This is neither of those things. And it's also not one step. It's 2 steps because we need to form an enolate again. So again, this chapter is all about enolates, right? We're using enolates a lot. So we need to form an enolate. So let's look at the mechanism of this. So if we take our addition product, so all right, so we have another alpha proton, right? Those alpha protons are acidic. So because we still have base floating around, that base can deprotonate our alpha proton again. So we form an enolate just like we did before. Okay, so we formed our enolate. Now that we've formed our enolate, we can eliminate out our OH. So we push our oxygen lone pair down, our carbon-carbon double bond hops over one position, and our OH minus leaves. Remember, OH minus is not a great leaving group, but we are in strong base, right? We are in strong base, and so it can leave in this case because we're in strong base. So we end up getting this alpha beta unsaturated aldehyde. So this is our aldol condensation product. And we regenerated our base. Okay. So normally when we have to eliminate out OH minus, it takes a while and you have to like push it and heat it quite a bit. Though in this case, it's actually much easier than in other cases. So why does this happen? It's because we are forming that conjugated system. All right, so this is why we wanted you to recall conjugation, because here we are making a conjugated system, right? So it's CC double bond, CC single bond, CO double bond. So double bond, single bond, double bond. So this is conjugated. So that means that it is stabilized. And so that drives that reaction forward. And so aldol condensation is actually the default. That's the one that wants to happen because that last step to form this conjugated system is driving it forward. So if you want it to stop at the addition product, you actually need to do something special. So when does condensation not happen? So there are two scenarios where condensation does not happen. The first is that you keep your reaction cold. So you specify that you're cooling down your reaction, normally like 6 to 8 degrees C. Could be colder than that, but that's usually what it is. Or if it can't happen. So let's look at an example where we have an aldehyde with only a single alpha proton. So, okay, if we do this in the presence of base, we can draw our addition product. So again, our electrophilic aldehyde becomes OH. Our nucleophilic aldehyde reacts from the alpha position. Okay, so this carbon right here is this carbon right here. And then our alpha position, right? Alpha position is right here. Okay, so we formed our addition product, looks like this. So notice we have two alkyl groups here, right? We have no alpha protons. So if you have no alpha protons, that means that you can't form an enolate again. And because forming the enolate is the first step of the condensation, we can't then do the condensation. Okay, so that's the other scenario, that it's not going to happen because it can't, right? It's not physically possible to do the mechanism, therefore it stops. Questions on that? Okay, so the condensation is the default. If temperature is not specified, you assume it keeps going. If you specify cold, then you can stop it at the addition product, okay? All right, so let's practice a little bit. So if you are given an aldehyde like this, You normally will only be given one aldehyde, but you have to assume that there's not just a single molecule in a flask, right? It can react with itself. Sodium hydroxide at 80 degrees C. What is that going to make? So in this situation, the first thing that I think about is like, okay, we've got an aldehyde, I've got a base, right? I'm definitely doing enolate chemistry. So what am I going to react with? Well, I don't have anything other than itself, right? So that's telling me that my aldehyde is going to be both my nucleophile and my electrophile. So therefore, it must be Aldol chemistry. So again, if I'm going to draw a product using an aldehyde as an electrophile, I know that that aldehyde is going to form an alcohol, and my nucleophile is going to be attached here. Okay, what is my nucleophile? My nucleophile is an enolate. So what does my enolate look like? It's going to react at the alpha position. So if I number my atoms here, 1, 2, 3, 4, 5, 6. I know that my nucleophile should be attached by this 3 carbon right here. 1, 2, 3. Good. And then I just need to fill in the rest of my carbons, which is 4, 5, 6. So that's how I would approach that problem. And then I check, okay, I did my aldol addition. Do I stop there? No, because this is specifying heat. So that means I need to keep going if I can. So then I check, do I have another alpha proton? Yes. Alpha proton, OH, we're going to eliminate. So then our final product is going to be the condensation product. This, keep numbering, 2, 3, and attached to carbon 3, I have 4, 5, 6. So that's my thought process when going through these types of reactions. All right, let's do a chime-in question to see if we can go backwards, because that's a little bit harder. So here, propose the starting material for the following aldol condensation. So I'm giving you the condensation product and the reagents. I want you to tell me what the starting material is. So it's always a little bit more challenging to go backwards, I think. So I highly recommend going one step back from the condensation product to the addition product, because I think it's easier to see. Feel free to chat with your neighbors, see if they're getting the same answers as you. Okay, maybe 10 more seconds, get your answers in. All right, let's see what we got. Okay, nice. So most people are getting it. The next most common is answer A, which totally makes sense. It's just counting your carbons. Please count your carbons, number your carbons. Very, very helpful. Okay, let's go through this to make sure that everyone knows how to approach this when going backwards. So I totally agree that it's harder to go backwards. So if you're asked for the starting material, you are given our conditions as well as this product. Okay. So the first thing that I look at in this case, right, is like, okay, I have that alpha beta unsaturated aldehyde. So that's the aldol condensation product. So what is the aldol addition product? So if I just go back one step, where does this come from? So that double bond, right, comes from having an OH on the beta carbon and a proton on the alpha carbon. So let's draw what that would be. Here, oop, I'm missing a methyl group there. Okay, so on my alpha carbon, I needed a proton. On my beta carbon, I need an OH. So that would be my aldol addition product. So just going one step back. And then from my aldol addition product, I know that my nucleophile is an enolate, which is that part. And my electrophile was an aldehyde, which was that part. So this is the bond that was made during the aldol reaction. So then I go backwards again. We're going to number our atoms here. 1, 2, 3, 4. 2. 1, 2, 3, 4. And then 1, 2, 3, 4. One, two, three, 4. And those two things are the same. So that's good. So that's how we kind of go step by step backwards. Okay, so you need to be able to identify that this is the bond that's being made, right, during that reaction, and that this part comes from your electrophile, which was an aldehyde, and this part comes from your nucleophile, which was the same aldehyde, right, just the enolate form of that. Questions on aldol addition, condensation, how to differentiate between them? Okay, so those are our first two variants of this reaction, aldol addition, aldol condensation. All of the examples that we've done so far have been aldehydes reacting with itself. So what happens if the two aldehydes are different? When can we react them? So that is called a mixed aldol or a cross aldol. So that is our next learning objective. We want to differentiate between reaction partners in a mixed aldol reaction, which is 21.3. And a mixed aldol reaction is sometimes called a cross aldol reaction, which just means that's two different coupling partners. So basically, your electrophile and your nucleophile are not coming from the same molecule or the same version of the molecule. So you can't just do this all the time, or at least not efficiently. If we were just to throw in two kind of random aldehydes, right? So these have different numbers of carbons. They each have alpha protons. So if we were just to mix those two things together, what do you get? A horrible mixture, right? Because both of them can act as the nucleophile. Both of them can act as the electrophile. So they can react with themselves. They can react with each other. It's all over the place. It's not great. Okay, so we don't like to do this. That you're not going to get an efficient reaction. You're not going to get like a one product in the majority. So this is very bad. So we want to devise a way of getting a single product, even when using two different partners. And by only one, I mean one major. You might have a little bit of some of the other ones, but one major product. So how do you favor one? So you need two conditions to be met. So both of these must be true. First, only one can form our enolate. If only one can form an enolate, you know what your nucleophile is going to be because it's the only one that can form the nucleophile. Okay. The second one, maybe a little bit trickier, is that the other partner, the one that can't form the enolate, is a better electrophile. Okay, so those are the two things that we need. So let me give you a couple of examples of how to make that be true. So if your electrophile is formaldehyde, okay, formaldehyde does not have an alpha carbon. Therefore, it cannot have any alpha protons. Okay. Formaldehyde is also a better electrophile than other aldehydes, right? Because there are no alkyl substituents, no electron donating groups. It's quite electrophilic. So formaldehyde is a very good partner for mixed aldehydes. And then we can basically use whatever aldehyde we want that has alpha protons as our nucleophile. Okay, so here we have alpha protons, which is good. So if we expose this to base, let's just give an example at 6 degrees. So that means that we are cooling the reaction, which means it's going to stop at the addition product. So our electrophile was formaldehyde. Our nucleophile was the other aldehyde. Let's number 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. And because it's cooled, it stops here. So this gives us a single product. Okay, so both of those conditions were true. Only one could form the enolate, and the other one was a better electrophile. The other common example of this is having an aryl aldehyde. So if I have an aryl aldehyde, right, this carbon right there has no alpha protons. Therefore, cannot form an enolate. Okay. And we know that aldehydes are more electrophilic than ketones. So if we react an aromatic aldehyde with a ketone that has alpha protons, then we should be able to do a mixed aldol. Again, sodium hydroxide, let's say 30 degrees this time. So I always draw my addition product first because I think it's easier to see. So my aldehyde turns into an alcohol. My nucleophile attaches from the alpha position, like so. Once I form my addition product, I check. This is heated. Therefore, we should keep going if we can. We do have additional alpha protons, so we need to do the condensation. So we need to lose our OH and one of our alpha protons to do our condensation reaction. And again, we get a single final product here. Yes. Yeah, great question. So yes, in this case, you actually have conjugation all the way into the ring, which is even more stabilized. Yes, absolutely. Yep. So yeah, aromatic aldehydes are very good electrophiles for this reaction. Yes. Yeah, that's a great question. Other questions on this? So these are mixed aldols when we're still using hydroxide as our base, right? So these are still conditions where we have equilibria kind of going on, right? So you need these two things to be true if you have all those equilibria happening. Yes. Correct. Yep. If you cool it down, it stops at the addition product and does not do the elimination. Yep, exactly. That's like one of the ways to stop it from doing the elimination because it wants to do that. Mm-hmm. Okay. So what if you want to make the aldol product where both of them can form an enolate, or that one of them is not a better electrophile? So that is the last kind of big variant that we're going to learn, which is using LDA. Okay, so now we need to identify when LDA is necessary for a mixed aldol reaction. Okay, so it's essentially, if we can't do it with hydroxide, then LDA is our solution to this. Okay, so it's when both partners have alpha protons. We want to form one enolate fully first, right? Because remember, we're using hydroxide as the base, right? We're forming a little bit of the enolate, and then that's like pushing the equilibrium forward by doing the reaction, but it's all in equilibrium. When we're using LDA, it is not in equilibrium. It is very much an irreversible reaction, so we can actually do it stepwise. So let me give you an example. If we have something like this ketone has alpha protons on the right side. So in the first step, we can mix it with LDA. So again, I'll draw out the structure of LDA. So this is diisopropyl amide, right? LDA. Okay, LDA is often also referred to as a non-nucleophilic base. Because these isopropyl groups right here are quite sterically bulky, right? So it doesn't like to attack things. It just likes to rip off a proton and then go about its day. Okay, so it's a non-nucleophilic base. Also, please note that in this case, it is not catalytic. Right, so this is stoichiometric base. So in the hydroxide case, we could use catalytic amounts of base. Here, it must be stoichiometric. And we are going to fully form that enolate. So our base is going to grab our alpha proton to form our enolate. So lithium as our counter ion, right? So this is full enolate formation. So it's going to sit in the flask as the enolate. Then, once you have fully formed that enolate, now we can introduce the electrophile that we want to add in. Okay, so this is a second step. You then add in your electrophile. So this electrophile, right, also has alpha protons. So if it would have been present from the beginning, it would have formed an enolate as well. So this is a next step. If you mix all together, you'll get multiple enolates. Okay, so it must be a second step. But now we have an enolate, we introduce an electrophile, nucleophile attacks electrophile. Okay, nothing has changed there. And we're going to double check and count our carbons. This is a very easy place to lose carbons. So 2, 3, 4, 1, 2, 3, 4. And then 1, 2, 3, 4, 1, 2, 3, 4. Then we still have our torpedo group. Okay. So again, it's going to sit there like this with the alkoxide because we don't have protons around because we're still in stoichiometric strong base, right? So then to get to our final product, we are going to do a third step. This is our workup step where we acidify to quench any extra base and to protonate our alkoxide. So again, next step. But in this case, we don't need to worry about the condensation happening, right? Because by the time we get to our addition product, we're not in base anymore. And so we're not gonna reform the enolate because now we're in acid. Okay, so this is another way of stopping it at the addition product, but this is a very steppy way, right? You basically don't want to do this unless you have to. So that's why most people use hydroxide as the base, because if you can get away with it, it's much easier to do. You can do it this way, it's just very steppy. That makes sense? Okay, so those are the different variants of the aldol. Addition, condensation, mixed using hydroxide, and then mixed using LDA. Okay, those are the four different kind of scenarios in which you can do this. The last thing I just want to point out is sort of the intramolecular variant. Again, it's not different. It's not actually a different reaction at all, but you can do this intramolecularly if you are forming 5 or 6 membered rings. So don't do this to form 3 or 4 membered rings, but 5 or 6 is fine. And it's going to be exactly the same mechanism because it's the same reaction. It just looks weird, right? You're going to form rings. And again, I very much recommend to count your carbons. So let's just look at an example. Like so. So we're going to number these 1, 2, 3, 4, 5, 6. Okay. So technically, we have 2 different types of alpha protons, right? We have the ones over here, kind of on the outside, on the methyl, or we have the ones on the inside. But the ones on the inside is going to form a 3-membered ring. So like that's not going to work. So we're definitely going to be deprotonating the outside one. So in the presence of base, we will form the enolate on the external alpha proton, because that is gonna what's gonna lead us to a 5 or 6 membered ring. So I have formed an enolate, right? So now I need nucleophile to attack electrophile. So where's my electrophilic site? Better be the carbonyl carbon. My nucleophilic site, right, is my alpha carbon on my enolate. So nucleophile attacks electrophile, break the weakest bond. Okay, let's number our carbons again. 1, 2, 3, 4, 5, 6. So this is going to form a 5-membered ring because carbon 1 is attaching to carbon 5. So I always draw my ring first. So 5-membered ring, and then I'm going to number my carbons. 1, 2, 3, 4, 5, and then I will fill it in. So on carbon 2, I need my carbonyl that got reformed. So let's draw a carbonyl at carbon 2. And then on carbon 5, I have my carbon 6 and I have my alkoxide. Okay, then I need to protonate to get to my addition product. Like so. Okay. Then, in this case, let's say that the temperature wasn't specified, so we assume it keeps going, right? We didn't cool it down, and we still have alpha protons here, so it needs to keep going. Still have alpha protons. So we're going to go again. So this is our addition product. We still have base around. So our OH minus is going to grab that alpha proton to reform our enolate, but now we're in a weird 5-membered ring, but it's not different. And then finally, we will do our elimination step, which is reform the carbonyl, CC double bond moves over, OH minus leaves. So it's exactly the same thought process as the intermolecular reaction. It's just intramolecular. So it looks a little different. You form a ring, but the mechanism is not actually different, okay? So all of these work exactly the same way. Even if you're forming these rings, just make sure that you're forming a 5 or a 6-membered ring because that's how it's stable. This one? Because it's the only one that will allow us to eliminate out, right? If I do it on this side, there's no leaving group here to be able to do the elimination. All right, thank you very much. That is the Aldol reaction. On Wednesday, we will do another enolate reaction.